Okay, so we just got introduced to a circuit analysis technique, which we refer to as node voltage. Okay, or we also refer to this as nodal analysis. Okay, node voltage method or nodal analysis. So what is node voltage method, right? It's simply a KCL done at a particular set of nodes, right? So we know that KCL involves currents, and when we try to do that in a slightly different format, then we get this node voltage. Okay, so let's say this is Vs, R1, R2, R3, R4, and R5. Okay, let's call this as an ideal source. Okay. So if you remember, one of the first things that we do when we try to solve a circuit with node voltage is to identify the essential nodes, right? As we discussed in the earlier lecture, essential node is anywhere where you have 3 or more elements that are connecting together, right? So that would be 2. And over here, this and this, they are essentially the same, right? This is the same. Because there is nothing connected between them, they are the same. Okay. Now what we'll do is, obviously these two are different, so we can refer to them as node A and node B. Okay. The last node, what we'll do is, just to reference our circuit, we'll mark it as our ground. So I'll go here and set this up as a ground voltage. Okay. Every node voltage expression or every node voltage circuit, when you set it up, should have a ground. Okay. Only then, we are referencing all the other nodes with respect to this. Okay. All right. So now what we'll do is, at each one of these nodes, we'll write the node voltage expression. Okay. So we'll do node voltage at A, node voltage at B. Okay. So if you do node voltage at A, okay, when we do node voltage at A, there are 3 branches connected to A, right? So just as you have in KCL, if you have 3 branches, you would write the corresponding 3 currents, or you would do the summation of the corresponding 3 currents. In this case, we'll write the current as a difference of voltage over the resistance. So here, if you look here, we assume that a current is flowing outwards from A. Okay, a current is flowing out from A. So in that case, that current will be equal to, if this is Vs, because at this point the same voltage appears here, and the voltage at A will assume to be Va. So if the current is leaving A, then it will be Va minus Vs divided by R1. So we'll go here and we'll set this up as Va minus Vs divided by R1. Okay. Same fashion, when we go here, we assume a current is leaving this node. Okay, so when the current leaves this node A, that will be Va minus, this is 0 divided by R4. Because if this is 0, the voltage here will also be 0 volts. Okay, so plus, you'll have Va minus 0 over R4. Okay, now at this point, I'll assume one more current leaving this way. Okay, so that will be Va minus Vb over R2. Okay, in general, whenever you write a node voltage expression, the node at which you are taking the voltage will always appear first. Okay, we assume that this is a higher voltage as opposed to every other node. So we'll always take the notation that the current is leaving this node, and therefore everything is positive. I have no negative values here. Okay, because I'm assuming the current is leaving. Leaving currents are always positive. Okay, so I'm assuming all the currents, when I consider A, I assume A to be at a higher potential than everything, so all the currents are leaving, okay, and so on, right? Let's do the same thing and move to B, okay? So we'll go here and say node voltage at B. All right, so when I do node voltage at B, at first I'll assume a current is leaving B. Okay, I want to assume that. So we forget about, we'll forget about everything that had to do with A at this point. Okay, we'll just ignore these directions. Now we are at B. So a current leaving B would be VB minus VA over R2. Okay, then we'll assume a current this way. Okay, which is nothing but VB minus 0 divided by R5. Okay, and finally we'll assume a current like this. Okay, in this case there is no other voltage over here. Okay, we don't have a voltage. Okay, but we know the current. Okay, so this current is actually flowing in opposite direction to the direction we assumed. Right, this is our positive direction. Okay, and IS is flowing in the opposite direction. So I'll just go here and say minus IS is equals to 0. Okay, negative IS is equals to 0. So these two are our node voltage equations, right? Typically, you will have a set of values to solve for or variables to find and so on, and then we can take the circuit forward to a conclusion. Okay? But the basic idea is as simple as that. Just be careful that the number of terms here, okay, so how did we define an essential node? We defined an essential node that any node that has 3 or more elements connecting, right? That means it should have 3 or more branches at that point. So whenever you write a node voltage expression, there should be 3 or more terms because each one of them refers to one branch. Okay, this refers to this branch. This is branch 1, branch 2, branch 3. Right? Same thing, 1, 2, 3. So there will always be 3 or more summations like this, right? Terms that refer to each one of these currents. The minimum is 3, otherwise it's not an essential node. Okay? So be mindful of that. If there is a expression that you're writing, make sure that you have 3 terms, and that's the minimum number. You can go up to any number of branches that are connected to that particular node. Okay? With that, let's take a, yes?
Why did you subtract IS?
Why did I subtract IS? Okay. So, as I said, whenever we take node voltage, our positive direction is, even with KCL, right? A positive current is a current that leaves the node, right? If you look at IS is entering the node. Okay? So always with KCL, there is a standard convention. It does not change from method to method. Whether you're doing KCL or you're doing node voltage or any other method, any current, okay, if I is entering the node, okay, if current is entering, it's a negative current. Okay, if I is leaving the node, all leaving currents are positive. Okay, just keep that in mind, and it is throughout the course. Okay, throughout circuit analysis, if you have a current that is entering a particular node, then it's with reference to that node, the current is negative. Okay, and leaving currents are positive. All right, so if you get practice enough just to write the equations or to set up the equations for node voltage, that is, as I said, 70% of the problem. The rest of it is just the numerical solving the equations and so on, right? So if you get used to this, that should be it. Okay, so let's go here and start with a very simple problem, and then we'll take it to more difficult levels. But to begin with, let's take a very straightforward question. Okay, this is a good one. Let's try this. You have 2 resistances. Okay, and here, like so, there is one voltage, 144 volts. 480, you have 10 ohms here, 3 amps, followed by 5. Use node voltage method. Okay. We need to use node voltage method to find. We need to find this voltage V1 and this voltage V2. Okay, find V1 and V2. Okay. All right. Find V1 and V2. Okay, so here we know that our two essential nodes would be, one node is this, okay? This will be, let's call this as VA, okay? And this voltage, let's call this as VB. Okay, that's node A and node B. All right, there are two distinct nodes because you have a resistor in between them, okay? Over here, we'll assume one of them to be our ground here. Or I'll just put the ground in between so that both the voltages are at 0. Okay. All right. So now it's straightforward. Let's go and write two expressions, okay, for each one of these nodes, and then from there we'll try to solve them. Okay. Once we know VA, VB, we'll be able to find V1 and V2. Okay. So here, when I do node voltage at A, let's say we do node voltage at A. Okay, when I do node voltage at A, I'll have VA minus 144. Okay, plus VA minus 0 over 10, right? Plus VA minus VB over 80 equals 0. Right? So what we'll do is, just to get rid of the denominator, okay, let's go here and we'll just multiply everything by 80. Okay. I'll multiply everything by 80 so that I can cancel out the 80 in everything else is a multiple, so right, plus 8 times VA, okay, plus, all right, so 20 plus 8, 28, and 129, right? So you have 29 VA minus VB, okay? That'll be equal to Similarly, try to write the node voltage expression at B. Okay, same way, just try to write the expression at B. So everything will be VB minus the corresponding end. Okay, so when you are at B, okay, VB minus VA divided by 80. Okay, here you have an incoming current, so you'll write this as -3 because 3 amps comes into. Then VB minus 0 divided by 5. Okay, each one of these branches, okay, one by one, you write them like that. So VB minus VA over 80, right? Then you have an incoming current. Any current that comes in is negative, so I'll go here and write -3. Okay. And then over here, so this point is 0, right? We want to take the difference between, this is 0, here you have 0 volts, right? So VB minus 0 divided by 5. Okay. To get rid of that 80, we'll once again multiply everything by 80. Okay, you can do it in any other way, but I find that easier to do. If you just get rid of the denominator, we can solve the equations easily. Okay. So here, when I multiply by 80, right? So this is 80 and 80 will get cancelled, so you will have VB minus VA, okay, time, okay, minus 3 times 80, okay, plus 16 VB is equals to 0. All right, so let's put together these terms. So you'll have minus VA plus 17 VB will be equal to 240. Okay? So we need to solve 1 and 2. You can do one thing, you can multiply this by 17 and add it, that way VB will get cancelled. Or you can multiply this by 29 and add it, that way VA will get cancelled. In either case, solve 1 and 2, and if you guys can tell me what is VA, VB. VA is 100 and VB is 20. Correct. So if you put it here, 2900 minus 20 will be 2880. Okay, correct. Okay. So now that we know these two values, we need to find VA, VB. Okay. So if you look at V1, okay, the value that we are trying to find, V1 is measured across this 10 ohm resistor, right? So that is nothing but the difference of these two voltages, because you're measuring across, just as we do in the lab. When we measure across, it takes the difference between these two voltages, right? So plus end subtracted from the minus. You take the plus end and then minus the negative end. So that will be equal to VA minus 0. Okay, so in this case, that will be VA, which is nothing but 100. This is 0, right? This end is 0 volts. Okay, so when you measure here, VA minus this terminal, which is 0, right? So that will be 100 volts. Okay, same thing with V2. V2 will be equal to VB minus 0. Okay, let's take this question, and this will have slightly more number of elements so that we can extend the node voltage equation. Okay, let's go with this. So here you have two current sources. Okay, there is no voltage, so 1, 2, 3. Let's, so here you have one resistance. Okay, and here goes that. Okay, here you have 1, 2, and 3 here. Okay, we have one source, another current source here. Okay, 15 and 5, so this is 15 amps. So what we are asked to find is, what are these voltages? V1. Okay, what is this voltage V1? This voltage V2, which is exactly the same last time's question, right? V1, V2. Okay, just as we did in the last problem, exactly the same thing. The only difference is you have another parameter to find, which is I1. Okay, so find V1, V2, and I1. Okay, so you guys know how to set up the equations. Okay, highlight the essential nodes. Okay, set up the equation and then we'll solve it again. Okay, once you set up the expression, as I said, 70% is just setting up these three equations. If you can set these up, then you know how to analyze the circuit. After that, everything is basically linear equations and algebra. Okay, so the important part is do it stepwise. Highlight the essential nodes, mark one as a ground, okay, and then write expressions with respect to those nodes. So here we have one node, right? This is going to be one of our nodes. Okay. Here you have one more node, okay, and this can be another node. Okay. Here, as you know, these are the nodes, okay. But essentially these are all the same, right? They are the same node. Okay. So you can mark any one of them as ground. It doesn't matter because they are all 0 nodes. Okay, they are all same nodes. Okay. When you have nothing connected between them, they are actually the same node. So the same thing applies here, right? This is the same node as this. Okay? So we can just use one of them. We don't need to use both. Okay? So I'll call this as VA. Okay? If this is VA, so will this be VA. Okay? And we'll call this as VB. Okay. Now, go ahead and write the expression. Keep in mind, at A, there are 4 branches, right? 1, 2, 3, 4, right? Let's say this is our first branch, 1, right? 2, you have 3, and then you have the 4th one. Okay, so there should be 4 terms 4 terms in your node voltage expression at A. Okay, let's also write node voltage at A, and let's do node voltage at B. A and B. Okay, so if you write it at A, incoming current, so that'll be minus 15. Okay, over here, I'll go here and say plus VA minus 0 divided by the resistance 60 plus VA minus 0 divided by 15. Okay, and over here, that'll be equal to VA minus VB divided by 5 is equal to 0. Okay. All right. So on this side, right, we'll start with VB minus VA divided by 5. Okay, then we go here, which is VB minus 0 divided by 2. Okay, and then this is a leading current, so plus 5 is equals to. Okay, so to get rid of the denominator, let's go here and multiply this by 60. Okay, same thing to get rid of the denominator here, I'm just going to multiply this by here. Okay, so that's going to be equal to 15 times 60 plus 60 will cancel, so only VA. Here, that will be 4 times VA, and 5 will be 12 times, so 12 times VA minus VB. Okay, so VA plus 4 VA, that will be 5 VA, plus 12 VA, so 17 VA. Okay, minus 12 VB. Okay, minus 900, okay, or 17 VA minus 12 VB is equals to 900. Okay, let's go to the side. So this will be 2 times, So 2 VB minus VA plus 5 VB plus 50 is equals to 0. So here you'll have you can multiply this by 2 and that by 17, so we can get rid of VA. And then you find VB. So from these two, we should get VA, VB. Any values for VA, VB?
VA 60 volts.
Yeah, 60.
VB 10 volts.
That's good. Okay, so just as we did in the earlier case, the voltage V1 will be VA minus 0. So V1 is nothing but VA, and V2 minus VB minus 0 would be V2. Okay. That is straightforward. Okay. There's nothing too complicated about it because you're measuring the voltage across this. That would be the voltage. Okay. So the only thing that's left for us to find is the current I1. Okay. Since I1 flows from A to B, okay, this is the higher voltage and that's the lower voltage. Okay. So high to low. Okay. So VA minus VB divided by the resistance 5. Okay. So in our case, that will be equal to 60 minus 10 divided by 5. So that will be 50 divided by 5, that will be 10 amps. Can I move the V1 and V2? Okay. All right. So if you look here, okay, V2 is this voltage, right? So just as you guys did with your experiment, if I'm measuring V2, I'll be measuring like this. Okay. So this is positive and this is negative, right? So the voltage at this end here, okay, at this end is VB. Okay, what is VB? VB we know is 10. Okay, voltage at this point is the same thing that we assume, 0 volts. Okay, so the total voltage is 10 minus 0. Okay, which is the same thing as VB.
How do you know VB is 10?
You solve these two to find VB, right? Solve equation 1 and 2.
You like answers.
This one, these two?
Yeah.
Okay, all right. So let me do one of these solving, so. All right, so let's take equation 1. It depends upon what you want to get rid of, which is either you want to get rid of VA or VB. So what I'll do is, I want to get, let's say I want to cancel out one of the factors. That's how you solve two linear equations, right? So we'll multiply something so that we can get rid of either VA or VB. Okay, so what I'll do is I'll take equation 1 and multiply that by 2. Okay, so if I multiply this by 2, 17 will be 34, right? So that is going to be equal to 34 VA. Okay, 2 times 12 will be 24, so minus 24 VB. Okay, and then 2 times 900 will be 1800. Okay, and then I'll multiply this by 17. Okay, so if I multiply the equation 2, multiply it by 17. Okay, so when I multiply 17, 2 times is 34. So that will be equal to minus 34 VA. And 17 times 7, right? So 49, 9 carry 4. Okay, will be equal to 7 times that. So that 17 times that, right? So 17 times that will be equal to 5. Sixteen is 80, so 17 will be 85. Okay? All right, so then we add these two. So when you add these two will cancel. Okay, minus 34 VA and plus 34 VA, they'll cancel. So now you'll be left with 24, so that will be equal to 5 VB, and that is 17, right? So that'll be 950. Okay? All right. So from here, once you know VB, you can find VA. Okay, so let's take this expression. Okay, if you have 2 VA plus 7 VB is equals to negative 50, right? We already know what is VB, so that will be equal to 2 VA plus, okay? So now what we can do is we can just move terms around, so VA will be equal to 70 and this is 50. So 70 goes here, it becomes minus 70, so that will be equal to 120. So VA will be equal to negative 120 divided by negative 2. Okay. So please practice solving the equations, otherwise you'll be stuck. Once we set up the equation, you will not know how to proceed. Whatever method is comfortable to you. I'll show you one more method. This one is easy if you have two variables. But if you have a set of three variables and three equations, okay, here you have two equations and two unknowns, right? VA, VB are two equations and you have two unknowns. But if it becomes three equations and three unknowns, we have to reduce them to two equations with two unknowns, solve them, and do that one more time. So let me show you another alternative, okay, where you can use this to quickly solve equations, whether they are a set of two or three. Okay. So these two equations, right? Let me put them here first. Okay. So what we'll do is we'll say 7. Okay. All right. So what we'll do is we'll represent this in a matrix form. Okay. So here I'll go here and set up a coefficient matrix. Okay. Coefficient matrix, we just write the coefficient of the variables. So this is 17 VA, so I'm just going to write 17 here. Okay. What is the coefficient of A here? -2. Okay. Here you have 12, and this is 7. Okay. And then we'll go here and we'll write this as VA, VB. Okay, that is these two parameters, VA. So when you multiply this, you get back the same thing. 17 VA minus 12 VB. 2 VA, 7 VB. Okay, is equal to the constant values. Okay, like that. So if I want to find VA, VB, all I have to do is simply take the inverse of this matrix. So you have VA, VB, okay, will be equal to okay. So all you need to do is figure out how to set up the matrix in your calculator. Type in the inverse, just press the inverse function, and you can multiply this. So here you'll get, once you multiply that, you'll get the corresponding values like this. So this will be equal to 10, I'm sorry, 60, and it means VA is equal to 60. The first value corresponds to VA, the second value corresponds to VA. Okay. So either of these two methods, this is a linear algebra method. Okay, this is using your linear algebra. Okay, this is if you want to do it with matrix inversion. Okay, either of them are perfectly fine. For less number of variables, this is a simpler method to do. Okay, if you have two variables and two equations, that's perfectly fine. But sometimes, as we go to the next set of techniques, you'll see that you'll have three sets of equations. For example, VA plus 2VB minus VC is equals to 5. Okay? Or you can have, for example, minus VA plus 7VB plus 2VC is equals to 3. And then you can have VA plus VB plus VC is equals to 0. Okay? We need to find all three. VA, VB, VC. We have three unknowns and three equations. Okay. One way to do it is to solve these two first, get rid of one variable, then solve these two, and then from them we can solve for one variable. Okay. We can do it like that if you want to use this technique. Or I can simply set it up as a matrix and find out all the values if you know how to do the inverse. Okay. So as I told you, that's straightforward from punching in the numbers in your calculator. So depending upon the model that you're using, you can just look up what's the function for it. Okay. So however you want to do it, it's fine, so long as you know how to solve it. Okay. For two variables, you can always do add and subtract, multiply with whatever is appropriate to get rid of the coefficients. But if you're not sure how to do that, just set it up as a matrix and take the inverse. Okay. Now, one concept that I want to share so that as you go forward and if somebody refers to a particular term, you should know what it means. Okay, so let's take a simple circuit, okay, and I'm just going to take, for example, a simple circuit like this. Okay, all right. Now, let's think of it in two ways, okay? So, for instance, I'll go in this branch, let's say this is I1, okay, and this is I2, okay? And I'll just say this is I3 for now, okay? And one more type of current that we generally see, we'll just go here and say this is some current I. So what are the main differences between these types of currents? Okay, so if you look here, I1 flows only has a limited length to flow through, right? Only in this length, this is I1. This is I3, right? Over here it's I2, okay? IA is all along this closed loop, right? So we refer to I1, I2, and I3 as branch currents because they only flow in a particular branch. Okay, these are branch currents. Okay, all right, these are branch currents. So if you are ever asked to find branch currents, that means you're asked to find currents that flow in individual parts of the circuit through each individual element. Okay, those are branch currents. Okay, because they flow through a particular branch. Okay. And IA, okay, because it flows in a closed loop, that's why you draw it like this, is known as a loop current. Okay, when we go to loop analysis or mesh analysis, after we finish node, we'll be talking about loop currents. Okay, so for now, just understand that branch currents, okay, branch currents are currents that flow like this. These are the branch currents. Okay, that flow in individual branches. Okay. Okay, so with that knowledge, let's try this question. Okay, probably this will be one of our. I think we have exhausted almost all types of questions. So let's try this. If needed, we'll try to. Yeah, let's try this question, and then. Okay, so here's our circuit. Okay, 3 resistances, 4, 5, 10. Okay, 2 like this. You have 2 voltage sources. Now in this case, we want to find all the branch currents, okay? So branch currents being the following. find all the branch currents. So, again, we need to use node voltage. Okay. All right, let's use node voltage. Let's quickly write the two equations, and from there we can find VA, VB. Okay, once we find VA, VB, everything should be straightforward. So let me explain here, okay? So let's take this as our ground, right? As always, we'll assume this is our ground. This point we'll say is our VA. This point we'll assume to be VB. Okay. We know the voltage at this node. This node is connected directly to 128. So the voltage at this point will be exactly 128 because it's the source, right? You're measuring here or you're measuring here. It's one and the same. There's nothing in between them. Okay. Same way, the voltage at this end, we know that that will be equal to 320 volts. Okay. So now you can directly write the expressions. Let me write the equations and then I'll show you how to find the branch currents. I'll let you solve the equations. Okay. So A and B should be, okay, so if we do node voltage at A, there are 3 branches there. So that will be VA minus 128 divided by the first resistance 4 plus VA minus 0, right, which is this, divided by 60, okay, plus VA minus VB divided by 5. Okay, we can multiply this by 60. Okay, to get rid of that denominator. Okay, so same thing. Node voltage at B. All right. Same thing. VB minus VA by 5. Okay, followed by VB minus 0 divided by 80 plus VB minus 320 over 10. Okay, we'll multiply this by 8. Okay, if you multiply that by 80, that will be 16 times, so this will be 16. Okay, 80 will cancel, so just VB and plus 8 times So this is going to be 16 plus 8, 24 plus VB, 25 VB. Okay, will be equal to 8 times 320. So 8 times 320 will be equal to 60. All right, so same technique here. 4 will be 15 times. Okay, plus VA and plus 12 VA minus VB should be equal to 0. Okay, so 15 and 1, 16, 16 and 12, okay, 28. Okay, and then there is 12 VB. Okay, will be equal to 128 times 15. Okay, whatever that is, you'll write that here. Okay, so we can, we can solve for VA and VB. So what I'm trying to show you here is the branch currents. Okay, so let's look at one. Okay, so if you're trying to find the branch current, let's say we are trying to find IA. Okay, so IA flows from 128 volts to VA, okay, through this 4 ohm resistor. Okay, so any current will be change in voltage divided by the resistance. Okay, any branch current or any current for that matter, I'll simply write it as difference between delta is the difference in voltage divided by the resistance. If the difference in voltage is 0, there is no current. Okay, so IA will be equal to, it flows from 128 to VA, so minus VA divided by the resistance, which is 4. Okay, so you can extend that to any particular branch current. Okay, so for instance, IB flows from VA to VB, so VA minus VB divided by the resistance. Okay, and so on. And that is what we'll do with our lab. So, by the way, the next lab experiment, the circuit looks exactly like this. Okay, this is the circuit. So whatever we are doing here in terms of writing, that will be our theory calculations. This is almost like our lab experiment too. Okay, only thing is you'll replace those resistances with your measured values, and the sources will be plus 5 volts or 10 volts or whatever.
Professor, assignment question.
You have an assignment? Okay. There was an assignment question that you guys wanted me to go over. If you have that question, please share that so I can. One of the assignment questions that, remember you were asking me last time? Okay, so please try this. I'll give you one question to Find VA, VB, you substitute the values, you'll get all the branch curves, okay? Please, just for your own practice, try to do it by solving equations, whether you try to prefer the matrix method or this, it's your choice. Okay, so it says, okay, the voltages we actually want at these nodes are as follows. Okay, what we want to see here is at V1, we want to see 12 volts. Okay, this is V1. At V1, we want to see plus 12 volts. Okay, and at V2, we want to see 5. Okay, common, this is your common. Common means 0. Okay, and finally at V3, we want to see minus 12. Okay, so let me leave this here for a second and let me show you what it means to, we'll take an example with 2 resistors and then we can do this for this case also, okay? All right, so okay, let's take this. Okay. Let's say I have 10 volts here. And let's say this is R1 and this is R2. Okay, so the voltage across this will be V1 and the voltage across this will be V2. Okay. So if you think of this as a parallel resistance, when I add the 2 voltages, as we did with your lab also, right? V1 plus V2 should always be equal to 10 volts. Okay, that means since they are in parallel, if I measure the voltage here, or if I measure across these two, it should be 10. Okay, so these 2 voltages should add up to be 10 volts. Okay, now because the same current flows through all of them, right? Let's say 1 amp is flowing through this. Okay, so if 1 amp flows through this, 1 amp will also flow through this, right? So the voltage does not depend on the current because the current is the same. It depends upon the resistance. So if I have 10 ohms here, then 1 times 10 will be 10 volts. If I have 5 ohms here, 1 times 5 will be 5 volts. So it's in proportion to the resistance. Okay. So for instance, let's say I want to see, okay, I want to see 5 volts here with respect, if this is my ground, okay, if this is my reference or common, if I want to see 5 is half of this, right? So these 2 resistance should be equal so that the voltage will get divided equally. Only then you will see 5 volts here because this will be 5 and then the other voltage will be 5. Okay. So if both of them are equal, okay, if R1 is equals to R2, okay, V1 will be equal to V2. Okay. And therefore V1 plus V2 will be the same. So that will be 2 times V1 or 2 times V2 and that will be equal to 5 volts. Okay. So if I pick this as 1K and this also as 1K, okay, you can choose anything so long as they are the same. 1K, 2K, 100K, so long as they are the same. Okay. It depends upon the ratio of these 2. Okay. If I change the ratio, okay, let's say if I change the ratio and I make this R1 is to R2, okay, let's say I make this 1K, all right, or let's just take it like this. Let's take it simply, okay, 1 ohm, or let's take this 1 2 ohms and 3 ohms. Okay, you can add a K, you can remove a K, whatever it is. Okay, so what happens now? By voltage division, V1 will be equal to 10 times the first resistance, 2 divided by 2 plus 3. Okay, so this will be equal to 4 volts. Okay, V2 will be equal to 10 times the total resistance. This will be 3 divided by 2 plus 3. That will be equal to 6. So again, when you add them, it's 10 volts. Okay, so they got, the ratio of these two is nothing but 4 is to 2 is to 3. Right? The ratio of the resistances was 2 is to 3. If you look at the ratio of the voltages, V1 is to V2, 4 is to 6, right? Which is, again, you can cancel this, 2 is to 3. So they'll always keep the same ratio, okay? The ratio is always, the ratio of voltages is the same as the ratio of the resistances, okay? So now, all right, if you look here, the only difference is they have made this common, okay? They have made this common. That means, if you look, let me show you here, okay? Every voltage here is measured with respect to the common. So if I measure here, I'm getting negative 12. If I measure here, I'm getting plus 12. But if you consider this whole range, okay, it should be 24. Is it 24 or not? So if you, this is plus 12, and this is another 12. Right? So if you add this, it comes out to 24 volts, right? It's exactly the same. So if you look here, this is 12 in magnitude, this is 12. So the sum of this should be exactly equal to this, only then it will get divided in the same ratio. This is 12 and 12. So what you can say is R3 should be equal to R1 plus R2. Okay, only then you'll get 12 volts here and another 12 volts here. That way it will add up to 24. Okay? So the voltage here, if you look at this voltage, because it's directly measured with respect to the common, it's being measured right here with respect to the common. This voltage here is 5 volts. Okay, this voltage here is 5 volts. But this 12 volts is measured from here to here, okay? With respect to the common, you're measuring 12 volts here. So this voltage has to be 7. Right? This voltage has to be 7 because if this is 12 and this is 5, that means this is 7, right? Only then it will add up to be 12, as you can see. Okay? So if you consider this voltage to be, let's call this as a voltage V1 here, and this voltage V2 here. Okay? All right? And if you want, you can assume this to be V3. Okay? All right. So if you assume this to be like that, then R1 is to R2. The ratio of the two resistances should be equal to the ratio of the two voltages, just as in this case. Ratio of resistances is equal to ratio of voltages. Or I can say R1 divided by R2 should be equal to V1 divided by V2. Okay? We know what is V1, 7 divided by 5. Okay? So you should pick, there is no hard and fast rule as to what you should pick, right? You can have them as 2 is to 3, 20 is to 30, 2K is to 3K, 200 is to 300. Okay? Only thing is the ratio has to be the same. Okay? Whether you say 6, 4, 12, okay, and 19 or whatever. So long as the ratio is the same, you're good. Okay? So I can assume this resistance as 7 and this as 5. If I have this as 7 and 5, that's fine. Or I can say R1 is equals to 7K. Let's say I assume pick 7K. Or it can be a multiple of this. R2 will be equal to 5K. Alright? If R1 and R2 are 5, we know that R3 is equal to this, right? Because they are in 1-to-1 ratio. Okay? So R3 is the sum of these two. This will automatically imply R3 should be equal to 12K. Okay? I can pick anything as a multiple of 7. If I want to pick, I can pick R1 as 700, R2 as 500, okay? And therefore R3 will automatically become 12 now, okay? So just keep the same ratio, okay? So the idea here is, if you are given a circuit where you're trying to design a voltage divider, okay? It takes 24 volts and it divides it depending upon what your output requirements are. Okay, if you want 5 volts, negative 12, plus 12, and so on. Okay, so just take them in the similar ratio. Okay? So any one of these answers is fine so long as you keep the same ratio. You can multiply that by 100, 1,000, whatever you like. Okay, let's conclude here for today. We'll try to promote voltage with some